Hello, welcome to El Zoominario. Today we're very excited to welcome Alejandra Quintos. Alejandra is an assistant professor and Nellie McKay Fellow in the Department of Statistics at the University of Wisconsin-Madison. This year, she's also a visiting professor at UNAM, Instituto de Matemáticas. She completed her Ph.D. in statistics at Columbia University under the direction of Professor Philip Protter. During her Ph.D. program, she held a Fulbright grant, received the Howard Levine Outstanding Teaching Award, and she was one of the finalists of the 2021 and 2022 Presidential Awards for Outstanding Teaching by a graduate student at Columbia University. Before graduate school, she had a merit scholarship to major in actuarial sciences at the Universidad de las Américas Puebla, where she graduated summa cum laude and was valedictorian of her class. Alejandra was born and raised in Puebla, Mexico, and currently lives in Mexico City. She also loves running. She has run 8 marathons so far and is training for the next one. Thank you so much, Alejandra, for accepting the invitation.
Sure. Thank you for the invite, Claudia. It's a pleasure to be here, telling you a little bit about my research. So before I get started, I want to make a disclaimer. If you have taken a class in probability or statistics, like this might seem too vague. Well, not too vague, but not so formal. I sacrifice formality for intuition in this talk. And so let's see where it goes. But of course, everything I'm going to present can be properly formalized and without actions and everything. But I'm going to be giving more intuition in this talk. So with that, let me start. So let's think about deterministic times versus random times. What is a deterministic time? So let me start by this story. So my mom always puts her clock 10 minutes ahead of time so that she's never late to anything. So whenever I want to know the real time, I just have to do this. I take my mom's time, say 3:45, and then I subtract 10 minutes, and that's the real time. This is a deterministic time because a formula can tell me exactly what that time is. Unfortunately, there are and let me just write it out because in math, we like to represent words with letters just because it's easier. We don't have to spell it out, all the words real time. We can just substitute it for y. So I'm saying y is equal to x, which is my mom's time, minus 10. For every time I see my mom's time, I can know what is the real time. And this is a formula that holds exactly. That is a deterministic time. But what about random times? And by random, I mean some examples are, for example, the time between different calls. Because sometimes you might have to wait a minute, and sometimes you might have to wait 2, and sometimes maybe less than a minute. But you don't know exactly. There's no formula that can tell you, oh, you have to wait exactly 5 minutes. Or like in this case, you just subtract 10 minutes from the actual time. Another example could be the time between failure of light bulbs, right? Or the time between earthquakes. And with this last example, it would be great if we could know when something like this is going to happen, right? The main idea of this talk is that we don't know exactly when this type of times, random times, will happen, but we would like to predict them. And so how do we do that? Well, probability comes to the rescue. And now I'm going to be talking to you a bit more how we can do that. Let me start by, if you have taken a probability class, this is going to be super common for you. It's going to pop right into your head, the exponential distribution. Basically, the exponential distribution tells us in a way how often an event occurs. We might not know exactly when it occurs, but we have an understanding of the behavior of the event. That is basically also what a probability distribution tells us, is the behavior of certain things that happens random. And in the specific case of the probability of the exponential distribution, it will have a parameter called lambda, which means that if we put lambda equals 2, there will be, in average, 2 arrivals per minute, or the expected waiting time between arrivals is half a minute, if your unit of time is minutes. And let me give you a plot. Why do we care about this plot that I'm presenting down here? Because, well, it's a way in which we can understand the behavior of this random time, right? So, and I also wrote these things here I'll explain those in a bit. But here I plotted the probability density function of an exponential with parameter 2. And again, just to remind you, if lambda is equal to 2, it means that in average, there are 2 arrivals per minute, or you have to wait half a minute to see an arrival. But we can know more by this little plot. For example, well, I know that the probability that the waiting time it's going to be greater than 0, it's going to be 1, which is represented as all the area down here. If I were to compute the area that is below this curve, I could see that it would be equal to 1. And in like the way we regularly talk, this could also be interpreted as there's a 100% probability of the waiting time being bigger than 0. Or like if you were to take 100 experiments, the 100 of them will be bigger than 0. But that's like really trivial, right? Because we know that a time is always greater than 0. But let's see another example. So now, instead of writing waiting time, because remember, I don't like to write full sentences. I just like to write letters. So I'm going to write W. So the probability that W is greater than 0.5, if I were to take the area, this area here would be 0.37. Or if I were to take 100 times, 37 out of them would be greater than 1/2 of a minute. Similarly, with the followings, the probability between 0, that W is between 0 and 0.5, that is, the waiting time is between 0 and 1/2 of a minute, so this area is 0.63, whereas the probability that the waiting time is between 1/2 and 1 is 0.23. Of course, you can see that it is more likely that the waiting time will be between 0 and 0.5 than it is to be between 0.5 and 1. And then finally, we have a really rare event, right? The probability that you would have to wait more than 2 minutes to see the event, which is the last line. And this line, it says that the probability that W is greater than 2 is 0.02. Or in other words, if you were to repeat the experiment 100 times, you would only have two of those times being greater than 2. And now let me move on to, let's say that we want to see successive arrivals. So instead of waiting just for one event, we are going to wait for a series of these events. But the thing is that each one of these events will follow an exponential distribution. And then here you have another exponential distribution. And here you have another exponential distribution, which is the behavior. If you are not familiar with distributions or probability, think of the exponential distribution as the type of behavior that the random time that you are observing follows. So in this case, the inter-arrival times are independent. That is, the fact that this guy arrived here does not influence this event. And at the same time, these two events do not influence the third event. And independence is a really important concept in probability. And in this example, that is something I am assuming. Also, another thing is that if you remember in the previous slide, let me go back, I was telling you about this lambda. This lambda is also known as the rate of arrival, because it's telling you, as this interpretation says, how often an event happens, right? But you can see that no matter where I am in time, this lambda is still equal to 2. That is what I mean in the next slide as the rate of arrival is constant. And so I'm introducing all this because part of my research, which is what I want to convey you today, what I do, right, for a living, part of my research is to study certain cases when this arrival rate is not constant. So now I can assume two things. Like, remember, lambda represented my arrival rate. You can, instead of writing lambda here, you can write arrival rate. We can study the case when the arrival rate depends on time. So as time goes by, you have more or less arrivals. For example, let's think of a cashier, right? Maybe during lunchtime, they will have more people, and that depends on time. But then when classes are in session, there are not that many people arriving. So that arrival rate depends on time. The other case, the one in which I mostly focus on, I'm writing it in this way, but what I want to convey is that this arrival rate is random. So now it's not only going to depend on time, but also it's going to depend in a random way. Like, we don't know exactly what arrival rate is. We don't know its exact value, but we can understand under certain conditions the way it behaves. But you might be wondering, well, that's really not the title of your talk, right? Because the title of my talk is modeling random time with phases. Where are the phases in all this? Well, I wanted to give this a brief overview to move on to the next topic. So in this case, and I want to highlight this, is that I have different arrivals. They are all independent, and we can think of them as different subjects. We can think of them as the time a train arrives. This is one train, this is another train, and this is a third train. But what if we are interested in just one person, which can go through many phases? That has to do with the title of my talk, right? So now I'm going to focus on modeling random time with phases. So suppose we have phases or states. This is really common, say, in insurance. Like they want to know how much time it takes you to move from one phase to the other. And here, I'm going to write on this slide so that we go slow. So say that you have 4 states. Healthy, a person can be healthy, sick, in recovery, or dead, right? Or in the dead state. So from healthy, I can move to the sick state, of course. And I'm going to assume that from healthy, I can suddenly go to the dead state if maybe I had an accident. Now let's see. From sick, I can go to recovery, and I could also go straight to death. But I'm gonna assume, and this is my prerogative, I'm gonna assume that from the sick state, you cannot go to the healthy state. So there's no way back. But now let's see the recovery state. I'm gonna assume that from recovery, I can go back to sick, and from recovery, I can go back to healthy. And once again, I'm gonna have the prerogative of assuming that from the recovery state, I cannot go to death. And of course, if I'm dead, unfortunately, I cannot go back to any of the other states, right? And so how do I represent this mathematically? Well, I'm going to represent this mathematically with a table that I'm going to fill out down here. And so before some things I need to mention, let's assume that the time unit is years, and perhaps I'm going to be a bit catastrophic, but I just want to convey the idea of how this works. Another thing I should mention is that if you are considering one person, and this person goes from healthy to sick, and then from sick, say, to recovery, and then from recovery to healthy, each time it gets to a different state, that person forgets what happened before. So if I move from sick to recovery, I don't care that I was like healthy at some state. Like you only remember what is happening in the present. So you really don't have memory. You just go as time goes by. And another thing I should point out is that this dead state, because I cannot get out of it, it's known as an absorbing state. Okay. So now let's start filling out the table. Let me assume that every time, well, not let me assume, but every time, like whenever I write something here, that represents in a way the time that a person spends in the healthy state, okay? And okay, we said by these arrows that if someone is in the healthy state, they can go to sick or to the dead state. And let me assume, and here's where I'm catastrophic, is that they have a probability to go to either of those. So they have half probability to go to sick or dead. And I would also, like, I know that they cannot recover because they are healthy, so I would put here a 0. And here comes one rule that it's because of the math that I'm not gonna go in great detail, unfortunately. But the rows have to add up to 0. So here I'm gonna write -1. And this -1, as I mentioned earlier, it represents the amount of time that you spend in the healthy state. Another rule, and you might be wondering, why are you writing this with a negative sign? It's another of those rules that I need so that mathematically everything makes sense. So just trust me on this one, but you can think of this as the time you spend in the healthy state, and then this and this, the probability that you have from moving from the healthy state to the sick state, and then from healthy to the dead. And with that same reasoning, let me complete the table. So from sick, I know I can go to recovery or to death. So I have 0.5 and 0.5 probability of going to either of those. That doesn't need to be the case, but just for simplicity, I'm doing this. And from sick, I cannot go to healthy. And then here again, -1, because remember that rule that the rows have to add up to 0. And then if I'm in recovery, then I have half the probability of going to healthy and half the probability of going to sick. And I cannot go to the dead state. So that's it. And again, here -1, because rows need to add up to 0. And here I will just put 0, 0, 0, because once I'm in the dead state, I cannot move anywhere else. Okay. So these things are known as Markov-John processes. And in the next slide, I'm going to copy this exact same table in the next one, just so that I can keep telling you about this and I have more space. This matrix is a lot of times represented as lambda. This matrix that I just, and now I said matrix, but if you don't know about matrices, you can think of it as a table. This table is represented as lambda. And if you were paying attention, you might have noticed that I always started in H, in the healthy state. And that could be represented in math as 1, 0, 0. I never start in the absorbing state, namely the dead, because then I cannot move anywhere. And that's not an interesting process that we would like to see how it behaves, right? Because if you are dead from the beginning, well, it doesn't make a lot of sense. But say I could start at a different state. I could start in the 6th state. And so this would be represented as 0, 1, 0, right? And I can also make it a tiny bit more complicated. And I could start randomly, meaning I could start with 1/3 probability, so 33.333 out of 100 times in the healthy state, then 1/3 in the 6th state, and 1/3 in the recovery state. And remember, we like to, or instead of calling the place that I start in math, we like to label things with letters. So I can call these guys here, or one of these guys, as alpha. And these two, and I'm calling them like this because these two are precisely parameters of another distribution that I'll tell you in a moment about. Another thing that I wanted to show you, which I think is kind of cool, that I could simulate this process. Like I could, like say, a simulation is when you toss a coin at random, right? And you record how many lands heads or tails. So I could also simulate this process that I just explained to you. Like it spends a random time in a certain state, and then with certain probability, it moves to another state, and so on and so forth. Here, I should write the states. So remember, first state is healthy, then second state is sick, third state is recovery, and finally the death. So here, what I'm plotting is two, as we know them, sample plots. So how the process behaves. So let's look at them more closely. The first one starts in the healthy state. It started in the healthy state, but then at some time between 0 and 1, maybe it's like 0.3, it immediately died, unfortunately. Then I could have a more varied path, right? So the red one, here, it moves to being sick. And then it spent some time being sick. After 2, then it went to recovery. And it spent some time in recovery, but then it went back to being sick. And then unfortunately, it died. And I can do this simulation for many, many, many cases, and I can start being interested in different things. One thing in which I could be interested, for example, is in the absorption time. And by that, I mean the time a process dies. So the time it hits this state, right? And I might be running my simulation for multiple times, and I can be storing these absorption times. And precisely, this is the distribution I wanted to tell you about. These times, the absorption times, follow what is known as a phase type distribution. And what's cool about the phase type distributions is that we can use them to approximate any random time. So remember that I started my talk by telling you a bit about the exponential distribution. Well, if we have the right parameters, remember for the phase type distribution, which in a previous slide I introduced as lambda and alpha, if we have the right combination of them, we can approximate any random time. We can understand the behavior of any random time that it's out there. These parameters might be really complicated, but that's something we can do. So that's basically what I wanted to tell you about. Well, and let me finish by saying that also part of my research, besides working in what I said previously, is trying to understand these phase type distributions better. By that, I mean that I'm trying to come up with methods in which one could better estimate the parameters that are in these lambda, and alpha, if you are given a series of time and you want to estimate the parameters that model them. So that's one. Then the other thing is like, now let's assume that this lambda, which tells you how the process behaves, how it moves, will depend on time. So that as time goes by, you have a different probability of moving to different states, and you have a different, you will stay more or less time in a particular state, depending on time. So that's some of the things that I do for research. That's everything about the research part of the talk. Here's my contact info. But before I finish, I would like to tell you something about my culture. And this is a great time to tell you about this because it's September. September is the Mexican month of independence. So our independence was started on September 16th. And there's a dish that is exactly from the place where I'm from in Mexico, which is called Puebla. That is traditional of this season. It's called chiles en nogada. And I'll explain you a little bit about how it's made. I'm not such a great cook, so I'll just tell you what I know from theory. I'm not kind of someone that goes and does dishes, right? But I enjoy them. And actually, this picture that I put here is a chile en nogada I had recently. So it's a Mexican dish, which is made of a poblano chile. It's one of those big peppers that you've seen. And they make it in such a way so that it's not spicy. It goes through a process so that to remove the spiciness of it. And they stuff it with picadillo. And the picadillo is made of all these things and many more, depending on who you ask. There are as many, I read somewhere that there are as many recipes of chiles en nogada as families in Puebla, in my town, because everyone makes their own recipe for this thing. But it's basically ground meat, which could have pork and beef, panochera apple, which is a special type of apple, in Spanish manzana panochera, sweet milk pear, which is pera de leche, and criollo peach, durazno criollo. Also, some people put walnuts, pecans, and almonds, and a lot of other. And I know it might sound like a sweet dish, but it's actually an entree. It's the main dish of a meal. And not only that, but it's topped with a walnut-based cream. And these walnuts are specific walnuts called Nuez de Castilla. I think I have it on the next slide. And this walnut-based cream sauce is called nogada. And then they top it up with some pomegranate seeds and parsley. And there's a reason why this dish looks this way. And if you are familiar with the Mexican flag, you might have already noticed that it has the colors of the Mexican flag, which I'll talk in a bit. But as I mentioned before, this dish is traditional from Puebla, the state where I'm from. And it's even more traditional of a certain town called Calpan, which is the place where they grow many of these things. And they have a fair that lasts all August. And you can go and buy the ingredients, but I should warn you, it's really hard to make because you have to cut so many different things and you have to prepare. And then the nuez is not your regular pecan. It has a hard shell, and then you break the hard shell, and it has a little bit of skin, and you have to carefully remove the skin to only really keep the walnut. And so it's really hard to make. You can buy the walnut already peeled, but it's super expensive. And it's a dish that is from July to September. This is the season of the Nuez de Castilla, which is the nuez that you have to use to have an actual chile en nogada. If you go somewhere else in Mexico, for example, Mexico City, where I am at right now, you can find chiles en nogada all year round, but those are not real chiles en nogada because they probably don't have the Nuez de Castilla really fresh, which is the ingredient that you need. And here, the color represents the Mexican flag, green, white, and red. And the story goes, but it's a story. Many historians debate when I was like doing a bit of research to prepare this talk. Some historians debate that this is not the truth. Before I prepared this talk, I believe this was the actual truth, that this dish was prepared to entertain Agustín de Iturbide when he came to Puebla after the signing of the Treaty of Córdoba, which is basically when we actually achieved our independence. Because on September 16, we celebrate the start of our independence, but I think it lasted, I mean, history is not my strong armor, I'm not a mathematician, but I think it lasted 11 years. And then finally, when Agustín de Iturbide signed this treaty, that's when the independence was achieved. And so it is said that this dish was invented by nuns to offer him as a way of celebrating that independence was achieved. And here, another thing, the chile en nogada is so hard to make that I was playing around with ChatGPT, and I asked ChatGPT, make an image of a chile en nogada. And as you can see, it's kind of the same, but this is not really a chile en nogada because you can see the stuffing all coming out, and that should not be the case. Also, a chile en nogada, the traditional one, which is also a big debate, whether it should be, I think the word is breaded, it's called capeado in Spanish, but basically it means that they put it with a bit of, they pass it over some flour and egg, and then they fried it so that it kind of has like that little bread crust around it. And that's a debate whether it should be or it shouldn't be. This one that I took a picture of, it was capeado, but the one in the right is not, because you would have to see something like brownish here, but you can see the chile. So yeah, with that, I end my talk. Thank you so much.